Module 1, Lecture B, Learning Problems. By the end of this lecture, you will be able to differentiate supervised and unsupervised learning tasks in Scikit-Learn, identify classification, regression, clustering, and dimensionality reduction problems from examples, and frame a dataset using samples, features, targets, and evaluation splits. Learning problem families. Learning with labels. Supervised learning trains models using labeled data, where each input is paired with a known target answer. The model learns patterns that connect features, such as patient information or lab results, to the correct outcomes. Because it is guided by examples with answers, it can refine its predictions for new cases. In supervised learning, labeled tasks are usually either classification or regression. Classification predicts categories, such as whether something belongs to one group or another, while regression predicts numerical values. In both cases, labeled examples teach the model what kind of output to produce from the input data. In Scikit-Learn workflows, checking whether labels are available determines the type of learning task. If the data includes a target outcome, such as subscription renewal, it supports supervised learning, where models can be trained and evaluated against known results. Without labels, the goal shifts to finding natural patterns or groups in the data. Reliable, relevant labels are what make historical data useful for prediction. Unsupervised learning. Unsupervised learning uses data without predefined labels, so the model looks for patterns and structure on its own. In Scikit-Learn, this means fitting an estimator using only the feature data. For example, customer purchase and spending data can reveal natural groups, such as bargain shoppers or premium customers, based on relationships already present in the data. Clustering is an unsupervised learning method that groups similar samples based on their features, helping reveal patterns when there is no predefined prediction task. It can uncover meaningful subgroups in areas such as healthcare or education. Dimensionality reduction is another key technique that simplifies data with many features while preserving important structure, making it easier to visualize and prepare for further analysis. Unsupervised learning is useful when data has no clear labels or prediction target. It helps reveal structure, such as possible groups or simpler representations, but these results must be interpreted carefully because there is no known correct answer. In Scikit-Learn, unsupervised models are mainly used to explore patterns in data rather than predict predefined outcomes. Supervised versus unsupervised. Supervised learning uses data that includes both input features and known target outcomes, such as labels or values to predict. The model learns from these examples so it can make predictions on new data. In contrast, unsupervised learning does not use a target outcome. In Scikit-Learn, supervised estimators are trained with both features and targets, and their success is judged by how well they predict unseen cases. Unsupervised learning works with data that has no target labels, so the algorithm is not told the correct answers. Instead, it finds structure in the data, such as grouping similar samples or simplifying complex data for visualization. In Scikit-Learn, these models are trained using only the feature data, and their output is a grouping or transformation rather than a prediction. To decide whether a problem is supervised or unsupervised, look at the training data and the goal. If the data includes correct answers to predict, it is supervised learning. If it only contains observations and the goal is to find patterns or simplify the data, it is unsupervised learning. The same dataset can support either approach depending on the question. So framing the problem clearly is essential, because labels determine the algorithm, training process, and evaluation method. Python code, supervised versus unsupervised. This section compares supervised and unsupervised learning using the same iris measurements. It focuses on how the two approaches differ in their use of labels, how models are fitted, and what kinds of outputs they produce. We import key Scikit-Learn tools for a basic machine learning workflow. The Iris dataset loader provides sample data, KMeans supports unsupervised clustering, and logistic regression supports supervised classification. We also use accuracy scoring to evaluate predictions and a train test split tool to separate data for training and testing. We load the Iris dataset from Scikit-Learn, which contains flower measurements used for both supervised and unsupervised learning. We use the first two measurement columns as model inputs, and we also retrieve the species labels. These labels are needed for supervised learning, where the model learns to predict each flower species from its measurements. The code verifies that the number of feature samples matches the number of target labels, so each sample has exactly one target. If they do not match, it raises an error to prevent training or evaluation problems caused by mismatched data. The dataset is divided into training and testing sets using Scikit-Learn's train test split function. 30% of the data is kept for testing, while stratification preserves the original class proportions. A fixed random state makes the split reproducible, producing the feature and label sets needed for supervised learning. A logistic regression model is created with a fixed random state for reproducible results and enough iterations to support training. The model learns from the training features and their known labels, then predicts labels for unseen test data. These predictions can then be compared with the true labels to evaluate performance. This section introduces unsupervised learning using a KMeans model on the Iris dataset. The model groups the feature data into 3 clusters, using multiple initial starts and a fixed random setting for reliable results. After fitting the model, each sample is assigned a cluster label that identifies which group it belongs to. The example first reports the Scikit-Learn version and the dataset size, including its samples and features, to support reproducibility and context. It then contrasts supervised and unsupervised learning. The supervised model is trained with features and target labels and evaluated by its rounded test accuracy, while the unsupervised model is trained with features only. Finally, it shows the first 10 cluster labels to illustrate how the unsupervised model grouped the data. This script uses the Iris dataset to compare supervised and unsupervised learning. In the supervised example, logistic regression learns from labeled training data and is evaluated on a test set using accuracy. In the unsupervised example, KMeans clustering groups the data into 3 clusters without using labels. The main point is that supervised learning depends on known targets, while unsupervised learning looks for patterns on its own. Task types, classification tasks. Classification tasks assign each example to one of several predefined categories, such as spam or not spam, rather than predicting a continuous number. In supervised learning, a model studies labeled examples and learns patterns in their features, like words or sender information. It then uses those patterns to classify new examples by learning boundaries between categories that may be too complex for simple rules. Classification predicts categories rather than continuous values. In binary classification, the model chooses between 2 outcomes, while multi-class classification chooses among more than 2 categories. This distinction from regression is important because it shapes how the machine learning problem is defined. A problem is a classification task when the model must choose from discrete categories or decisions, such as admit, waitlist or deny, risk levels for loans, or labels for medical scans. Classification is not only about assigning labels, it also requires evaluating predictions in context, because different kinds of mistakes can have very different consequences. Python code, classification tasks. This example trains a simple classification model, which predicts categories rather than continuous values. The results include the predicted labels and the model's accuracy on test data. We import key Scikit-Learn tools for a simple classification workflow. The iris dataset loader provides a standard dataset. The train test split function divides it into training and testing data. And the k-nearest neighbors classifier builds a model based on nearby data points. Finally, the accuracy score function measures how well the model's predictions match the true labels. We load the built-in iris dataset from Scikit-Learn, a simple dataset commonly used for multi-class classification. Its flower measurements serve as the input features, and the species labels serve as the target values. This gives us the data needed to train and evaluate a classification model. Before training, verify that the number of data samples matches the number of target labels. This ensures every sample has a label, and if they do not match, raise an error to protect data integrity. We split the dataset into training and test sets using Scikit-Learn's train test split function. 25% of the data is held out for testing, and a fixed random state makes the split reproducible. Stratifying by the target keeps the class proportions similar in both sets, helping maintain a balanced distribution. We create a k-nearest neighbors classifier from Scikit-Learn using 3 neighbors, so each prediction is based on the 3 closest training points. After fitting it to the training data, the model learns how the input features relate to the target labels and is ready to predict categories for new data. The trained classifier predicts labels for the test data. Then its predictions are compared with the true test labels. The resulting accuracy score shows how often the model is correct on unseen data. To make the model's result easier to understand, the numeric class labels are converted into the iris dataset's category names. The true label for the first test sample and the model's predicted label are both mapped this way, so they can be compared as readable class names instead of numeric codes. The output summarizes a classification model run by showing the Scikit-Learn version, the dataset size, the number of features, and the available target classes. It then compares the true class of the first test sample with the model's predicted class. Finally, it reports the test accuracy, which indicates how well the model performs on unseen data. This script shows a simple iris flower classification workflow. It loads the iris dataset, splits it into training and test data, trains a k-nearest neighbors model using 3 neighbors, and evaluates its predictions with accuracy. It also converts the numeric labels into species names for one test example, then reports basic dataset details, the target classes, the test accuracy, and the Scikit-Learn version used. Predicting continuous values. Regression is used to predict continuous numerical values, such as house prices or temperatures, rather than categories. Unlike classification, it focuses on the size and meaning of numeric differences. This makes regression important for tasks like budgeting and forecasting, where the magnitude of a prediction supports better decisions. Regression uses examples with input features and known numerical targets to learn how to predict values for new cases. For example, data about homes, patients, or business activity can be used to estimate prices, hospital stays, or revenue. The goal is to make predictions accurate enough to support practical decision-making. A task is usually a regression problem when the model predicts a numerical value where closeness matters, such as a count, rate, score, or percentage. Counts can still be treated as regression targets when the goal is to estimate an amount. Regression models are evaluated by how near their predictions are to the true values, with attention to the size and pattern of the errors. Python code. Predicting continuous values. This example shows a basic regression task, where the goal is to predict numerical values rather than category labels. The results highlight the size of the prediction errors. We import key tools from Scikit-Learn to build and evaluate a regression model. The diabetes dataset provides the data. Linear regression creates the prediction model. Mean absolute error measures how far predictions are from actual values on average. And train test split separates the data for training and testing. We load Scikit-Learn's diabetes dataset, which is designed for regression. It provides input features along with a continuous numerical target, giving us the data needed to train and evaluate a regression model. To keep the regression examples simple, we use only the body mass index feature from the diabetes dataset. We locate that feature, extract its data in the proper two-dimensional form for modeling, and use the dataset's target values as the outcomes to predict. This prepares a basic one-feature regression task. Before training, the code verifies that the number of input samples matches the number of target values. This ensures every sample has one corresponding target. If they do not match, it raises an error to prevent problems during model training. We use Scikit-Learn's train test split function to divide the features and targets into training and testing sets. 25% of the data is reserved for testing, so the model can be evaluated on unseen examples. Setting the random state to 42 makes the split reproducible, producing separate training and testing inputs and targets for model training and evaluation. We create a linear regression model with Scikit-Learn, then train it on known data. During training, the model adjusts its parameters to find the best fitting line, reducing the difference between its predictions and the actual values. Use the trained model to make predictions on the test data. Then compare those predictions with the actual target values. The mean absolute error summarizes the average size of the prediction errors, giving a simple measure of model accuracy. Lower mean absolute error means the model is performing better. This section checks the Scikit-Learn version for reproducibility, then frames the task as regression because the model predicts numerical values. It evaluates performance using mean absolute error, which shows the average prediction error in the target's units. Finally, it compares one actual test value with the model's prediction to give a quick sense of how close the result is. This example shows a simple regression task using the diabetes dataset from Scikit-Learn. It uses body mass index to predict a numerical target, trains a linear regression model on part of the data, and tests it on the rest. The output reports the mean absolute error to show average prediction error, compares one true value with its prediction, and confirms that the task is regression because the target is numeric. Clustering tasks. Clustering is an unsupervised learning method that finds natural groups in data without predefined labels. It uses similarities and differences among features to form clusters. For example, an online retailer might group customers by purchase behavior, such as frequent buyers and occasional shoppers, based on patterns that emerge from the data itself. A clustering task is about discovering hidden groups in data, rather than assigning items to known categories. For example, it might reveal patient subgroups with similar symptoms, neighborhood mobility patterns, or song groups based on audio features. The key idea is that clustering is exploratory. It looks for meaningful patterns that were not defined in advance. Clustering can reveal useful patterns, but its results must be interpreted carefully because the groups are not automatically meaningful. Their value depends on choosing relevant features, measuring them appropriately, and matching the idea of similarity to the real-world question. Since clustering has no single correct answer like classification, domain knowledge and human judgment are needed to decide whether the groups are useful. A good clustering task begins with a clear purpose and treats the results as patterns to investigate, not final conclusions. Python code. Clustering tasks. This example demonstrates clustering without target labels. KMeans groups data points based on feature similarity, and the resulting plot helps show the clusters the algorithm inferred. We import the main tools needed for this clustering example: NumPy for numerical work, Matplotlib for plotting, and Scikit-Learn for machine learning. From Scikit-Learn, we use KMeans for clustering and a blob data generator to create synthetic data. These imports prepare us to generate data, cluster it, visualize the results, and check the library version. We generate synthetic data with Scikit-Learn's makeBlobs function, creating 180 samples with 2 features grouped into 3 clusters. A cluster spread of 0.75 controls how separated the groups are, and a fixed random state makes the results reproducible. This gives us a simple dataset for modeling situations where the true group labels are not known. Before clustering, the code confirms that the feature data has the expected shape: 180 samples with 2 features each. If the data does not match this format, it raises an error. This check helps prevent problems by ensuring the input is valid before applying the KMeans algorithm. We configure KMeans to group the feature data into 3 clusters, using a fixed random state and multiple initial starts for more reliable results. After fitting the model without target labels, each data point is assigned to the cluster it most closely matches, and those cluster labels are saved for later analysis. Use NumPy's bin count function on the cluster labels to find how many samples are in each cluster. Setting a minimum length of 3 ensures all clusters are included, even if one has no samples. The counts are then converted to integers and joined into a comma-separated string for easy display or logging. The code reports the Scikit-Learn version to support reproducibility, then summarizes the input data as 180 samples with 2 features and no target labels. It then shows the cluster sizes found by KMeans, giving a quick view of how the algorithm grouped the data. A scatter plot is created to visualize the KMeans clustering results. The first 2 feature columns provide the horizontal and vertical positions, while each point is colored by its assigned cluster using the Viridis color map. This makes the inferred groups easy to distinguish visually. To show the KMeans cluster centers, plot their coordinates from the model's cluster centers attribute using a scatter plot. Make them stand out by using red X-shaped markers that are larger than the regular data points, and add a legend label so the centers are easy to identify. The plot is labeled to show that clustering can find groups without known labels. The axes identify the 2 features being compared, and a legend helps distinguish elements such as cluster centers. Displaying the plot lets us visually interpret the clustering results. This script shows how KMeans clustering in Scikit-Learn can find hidden groups in data without using labels. It creates a small 2-feature dataset with 3 underlying groups, applies KMeans, and reports basic information such as the Scikit-Learn version, data summary, and cluster sizes. A scatter plot then displays the assigned clusters, with red X markers showing the cluster centers, making it easier to see how KMeans groups similar points together. Data framing, samples, and features. For machine learning, a dataset should be organized into samples and features. A sample is one instance, such as a patient visit or property listing, while features are the details that describe it, such as age, symptoms, size, or location. This structure makes clear what the model is learning from and what it may predict. In Scikit-Learn and many machine learning workflows, data is stored as a feature matrix, where each row represents one sample and each column represents one feature. This structure keeps the meaning of each feature consistent across all samples, whether the data comes from customer transactions, satellite images, or another source. Consistent representation is essential because every sample must use the same columns in the same way to avoid errors and confusion. In supervised learning, the target is the value the model is trained to predict, while features are the input information used to make that prediction. Targets may be categories, such as spam or loan default, or continuous values, such as house prices or energy use. Features must only include information available at the time of prediction, because using future information creates data leakage. Clearly defining samples, features, and targets helps the model learn from the right data and perform reliably in real-world use. Python code, samples, and features. Treat each row of the data as one learning sample. Separate the descriptive features from the target labels. Then, evaluate the model using distinct training and testing splits. We import pandas to work with tabular data and use Scikit-Learn's train test split tool to divide the dataset into training and testing parts. This split helps us train the model and then evaluate how well it performs on separate data. We create a small in-memory dataset with pandas using a data frame, which stores data in a table-like format. The table is built from columns for home area, number of bedrooms, distance in kilometers, and price in thousands. This structure makes the housing data easy to organize, manipulate, and analyze with pandas. We prepare the dataset by separating the input features from the value we want to predict. The features are area, number of bedrooms, and distance, while the target is the price in thousands. This separation lets a machine learning model learn how the features relate to the target price. To prepare the housing data for machine learning, we separate the input features from the value we want to predict. The features are the home's area, number of bedrooms, and distance, while the target is the price in thousands. This clear split tells the model what information to learn from and what outcome to predict. Before training, confirm that the feature data and target values contain the same number of samples. This ensures every sample has a matching target for supervised learning. If they do not match, raise an error to stop processing inconsistent data. The train test split function in Scikit-Learn divides the features and target values into training and testing sets. Here, 1/4 of the data is kept for testing, and a fixed random state of 42 makes the split reproducible. The result is separate training and testing data for both the features and the target values. The dataset is framed as a supervised regression problem. We summarize its size by reporting the number of samples and features, list the feature names, and identify the target variable. We also report how many samples are in the training and test sets. Then preview the first 2 rows of the feature data in a clean display. The script creates a small housing dataset for a supervised regression task, using features such as area, bedrooms, and distance to predict price. It separates the input features from the target values, then splits the data into training and test sets, with most samples used for training and the rest for evaluation. It also prints a brief summary of the dataset, including the number of samples, features, and a preview of the feature data. Train, validation, test. In machine learning, data should be split into training, validation, and test sets. The training set teaches the model patterns, the validation set guides model choices, and the test set is saved for the final check on new data. Keeping these sets separate helps show whether the model truly generalizes instead of just memorizing past examples. Data splits help evaluate a model fairly. The training set is used for learning, the validation set helps refine the model, and the test set is kept untouched until the end. Using test results to adjust the model can make performance look better than it really is, so the test set must stay separate for a reliable final check. Choose data splits that match how the model will be used. Random splits often work for ordinary tabular data, but time-based data should train on earlier periods and test on later ones. For grouped records, keep each group in only one split, and for rare classes, make sure they are represented well enough to support a meaningful evaluation. Python code train validation test. This script shows how to split data for honest model evaluation. It explains the roles of training, validation, and test sets, while highlighting split sizes and class balance. We start by importing Scikit-Learn tools needed for a basic machine learning workflow. The Iris dataset loader provides a standard classification dataset, and the train test split function divides the data into training and testing sets, so model performance can be evaluated. We load the built-in Iris classification dataset from Scikit-Learn, a simple dataset often used for demonstrations. Its flower measurements are used as the input features, and the Iris species are the target labels to predict. This prepares the data for later steps, such as splitting it into training and testing sets. Before training or evaluating a model, confirm that the feature samples and target values have the same count. Each sample must have exactly one matching target, and if the counts differ, an error should be raised to prevent data mismatches. The dataset is split into a training and validation portion and a separate test set using Scikit-Learn's train test split function. 20% of the data is held back for testing, with stratification to keep the target class distribution consistent. A fixed random state makes the split reproducible, and the untouched test set is saved for the model's final evaluation. The remaining data is split into training and validation sets using Scikit-Learn's train test split function. 25% is reserved for validation and 75% for training. Stratification keeps the class balance consistent, and a fixed random state makes the split reproducible. Count the samples by measuring the size of the target data. The full target set gives the total number of data points, while the training, validation, and test target sets show how many samples are used to fit the model, tune it, and evaluate its final performance. We first report the Scikit-Learn version to support compatibility and reproducibility. Then we summarize the dataset by showing its total number of samples and features. Finally, we give the sizes of the training, validation, and test sets, which are used for model fitting, tuning, and final performance evaluation. To check that stratification preserved class balance, calculate the percentage of each class in the training, validation, and test sets. For each split, count how many samples belong to each class, divide by the total samples in that split, and convert the result to a percentage. Comparing these percentages confirms that the splits keep the original class distribution. We check the class percentages in the training, validation, and test sets to confirm that each split preserves the original class balance. This helps ensure the validation and test data are representative of the full dataset. The test set is kept untouched until final evaluation, so it can provide an unbiased measure of model performance. This script shows how to split the Iris dataset into training, validation, and test sets while preserving class balance through stratification. It first sets aside 20% of the data for final testing, then divides the remaining data into training and validation portions. The script checks basic dataset information, reports the split sizes, and compares class percentages to confirm that each set stays balanced. Keeping the test set untouched until the end supports a fair final evaluation of model performance. Baselines and limits. A dataset needs a simple baseline so we can judge whether a model is truly learning. For classification, this might be predicting the most common class, and for regression, predicting the average value. These baselines set a minimum standard because a complex model that cannot beat them may not be useful. They also help make performance results more meaningful and support responsible data framing. When using baselines, remember that datasets capture only part of reality. Too few samples, missing features, inaccurate targets, or unrealistic data splits can make results misleading. A model may fail when real-world conditions change or when important factors were not included in training data. Always check that the dataset matches the intended use and evaluate the model in the context where it will actually be applied. Baselines help show whether a model improves on a simple standard, but they do not prove the model is ready to use. Evaluation also depends on whether the dataset reflects the real conditions the model will face, including important sources of variation. If performance changes across settings, such as different hospitals, the score must be interpreted in context. Reliable machine learning requires both a meaningful baseline and a clear understanding of the dataset's limits. In this lecture, you learn to differentiate supervised and unsupervised learning tasks in Scikit-Learn. Identify classification, regression, clustering, and dimensionality reduction problems from examples. And frame a dataset using samples, features, targets, and evaluation splits. In the next lecture, Lecture C, we will go over configuration basics.
Thank you for your attention. See you all in the next lecture.